In 1909, Charles Barkla, he studied what happens when you shoot an X-ray at a metal or some material, and he found that the metal gives out X-ray that produces a line spectrum in a way that is quite similar to the hydrogen spectrum. Let's take a look at how this is like. Okay, suppose there is a glass tube. Suppose we have a glass tube, and let's look at how X-ray can be produced. Need a glass tube with a vacuum inside. Okay, and we need a negative and a positive metal plate, and say a high voltage connecting them, maybe as high as say 1,000 volts or more. This would produce a beam of electrons with a high velocity, the high kinetic energy, and when this kinetic energy, when this electron hits the metal, can be any metal. For let's see. For the example that I would mostly be looking at in this and maybe the next video, the metal that I use is called molybdenum. Right? Not sure what's special about this, but it's just a common example that I found when I searched on the internet. Okay, so but it can be any other metal, just some metal on the positive pole. When this beam of electron hits the positive plate, the kinetic energy of the electron would apparently be converted to X-ray. So X-ray would start coming out from the positive plate when the electron hits it. So these are X-rays. So 1909 was the very early days of X-ray. I think not long after it was discovered. So this was one of the very first research on X-ray, and what Charles Barkla did was he wanted to look at the X-ray spectrum. Now, if you remember, for the hydrogen spectrum or for visible light, we could use the diffraction grating, very narrow slits, very closely spaced together, and observe the fringes and measure the wavelength by measuring the fringe angles. Now, and let's see, I think in an earlier video, in an earlier video I must have talked about, when I talked about how when I talked about how electrons can behave like waves. I talked about how because the wavelengths are about just as long as the size of an atom, we need to use the atoms themselves in the crystal as the diffraction grating, and it's the same for the X-ray. Right? In a moment, I shall describe a little bit more about the typical wavelengths and energies of the X-ray photons. But for now, let me just say that in order to observe the spectrum, what is needed is what is needed is to have a piece of metal, usually. Well, it doesn't have to be metal, just a piece of some crystal where the atoms are arranged in a regular order. So usually some kind of crystal that would act as a diffraction grating. Okay. So with this crystal, when the X-ray comes through, the X-ray will be diffracted in different directions. Now, usually, X-rays coming out from this plate would have a range of wavelengths, so we can have X-rays diffracted at different angles. Remember that the angles and wavelengths are related by this formula, d sine theta equals to lambda, the diffraction grating formula. I've taken the n here to be 1. Okay, so by measuring the angle, it is possible to relate it to the wavelengths. So, and I suppose in those days, in the very early 1900s, the simplest and maybe the only way to detect the X-ray in those days is to use a photographic film. So down here, so it wouldn't be a piece of white paper where we can look at, say, the colors of the rainbow with our eyes. Right? We can't see X-ray. It's very extremely high frequency, beyond the visible spectrum. And the way to observe it would be, for example, to use a photographic film, not the digital cameras of today, but a real traditional film with a layer of film chemicals that will change color, or that would have a reaction when light falls on it and can be developed. So with this, it is possible to observe how the different wavelengths of the X-ray coming out from this metal plate spreads out into different wavelengths. So for what I'm going to talk about, and from later work where the technology becomes more advanced and it's possible to actually directly measure the intensities of the X-ray coming through at different angles. Today, it is actually possible to plot a graph. So I'm going to show the spectrum as a graph. Now the horizontal axis would be, I would take that to be lambda in nanometers, and now typically the spectrum would look like this, right? With some peaks that corresponds to the lines on the spectrum. Okay, so at certain frequencies, there would be a sharp peak, that means a much higher intensity. And that's a bit like the line spectrum, say for hydrogen, where the lines on the line spectrum correspond to the wavelengths that are present. This would be intensity. Okay. Now these peaks here would, if you look at it on the film, would probably show up as lines on the film. Okay, where we have a higher frequency there. Let me just number this 1, 2, 3, 4 for the time being. Okay, and it would probably give you lines here 1, 2, 3, 4, right? 1 to 4, and there would be a kind of a background that would show up as some lighter color that's lighter color that spreads over, maybe not color, but a lighter shade of gray that spreads over the whole film. So in this sense, what Barker found was that when X-ray is emitted from a metal, he would have seen line spectrum just like for hydrogen atom. And like the line spectrum for hydrogen atom, the pattern of the lines, the position of the lines are different for different elements. Like sodium would have a different set of lines from hydrogen. So in the same way, Barker found that if he used a different metal, say instead of molybdenum, he used, say, copper or iron, he would see different lines. He would see lines in different positions. So that means that like the case of line spectrum for hydrogen, it is possible to use this X-ray spectrum to tell what the element is, and that's actually what people have used in later years. And because the exact positions of the line is different for different metals, it is described as characteristic X-ray spectrum. Characteristic in the sense that it is a particular spectrum would correspond to a particular metal, would be characteristic of that particular metal.